Today we're going to learn about superconductors, and we're going to do it with hands-on demos. We'll talk about superconducting magnetic repulsion and also magnetic flux pinning and levitation. We'll show how a superconducting levitating train can go around a circular track. We'll finish up with talking about how superconductors were discovered and also the theory of how they work. Welcome back. Today, one of the most exciting phenomena in science. We're going to talk about superconductors and superconductivity. Now, I actually worked in a university lab for many years actually making from scratch superconductors and synthesizing them. So this is something I'm passionate about. I can't wait to share this with you. Now, a superconductor is a device or a chemical that loses all of its electrical resistance below a certain temperature. We'll talk a whole lot about the theory in just a minute. Now, I would like to show you some of the incredible effects that you get from a device or a material that has no electrical resistance. All right, we have our superconductor nice and chilled, and what I'm going to do is drop the circular magnet on it again from a little bit higher up to force the magnetic field to go inside, and let's see what actually happens. And you can see in this case, the magnetic field is not repelled anymore. It found one of those defect zones, and the flux from this tiny little magnet is now pinned inside, and it really can't move. If you try to push it, you can get it to deflect. See how I'm pushing it left and right? I'm kind of pushing it back and forth. It's kind of going back to the same place. If you see it kind of going down to the surface, it just found a defect zone closer to the surface, right? If I physically bring the magnet close and force it and then just let it go, you'll see it'll levitate there. Now again, sometimes it's trying to repel the magnetic field. Depends on if it found one of those little defect zones inside here. And we'll go from there. So to do the levitation, I'm going to push it really close, force the field lines in, and then let it go. And you can see it's actually spinning very slightly there as well. I have some iron filings attached to the side of it. That's why you can see it spinning there from a previous experiment there, right? So it's not magic. What's really happening is the magnetic field is trapped inside the superconductor. So it initially doesn't want to let any in, but if any does get in through a defect zone or an imperfection, then the surrounding superconducting material generates eddy currents in the material that create a magnetic field that physically lock the flux lines from that magnet in place, and so it can't move. Now, if you push it hard enough, it'll move, but in general, if I give it a little nudge in either direction, it doesn't really want to move. All right, let me take that one out and do a little bit of a bigger magnet here. Let me add a little bit of coolant here. All right, here we go. So now what I'm going to do is I'm going to drop this thing from a height and see if I can get it to lock in place. Camera, I hope it looks really cool, but in person, it's just, it looks like magic. I can't even describe it with any other word other than that. It looks like magic, right? If you push it, you can get it to move, but it wants to spring back into place. The magnetic field lines from this magnet are locked into place. And in fact, I can physically move it and make it change orientation and make it lock in a different orientation. So I'll push it this way, for instance, and then I can see it locking like that, right? I can grab it and remove it, and then I can physically place it back and try to get the field lines to lock in place horizontally like this in a different orientation. If I apply a little force a little bit lower, it'll lock lower. If I try to tilt it up, it'll lock in a different orientation if I can get it to do it. They're kind of finicky. You get the idea. As I move it around, I can get it to lock in different orientations vertically. Now that was a circular magnet. Actually, I think the most impressive one are the square magnets that I have here. And the reason they're more impressive is just because you can see them spinning a little better. So here I have just another magnet, and this one is square. Let me see if I can get it to go perfectly horizontal. And of course I can't. All right, let me see if I can get it to lock in place perfectly horizontally. I got to push it kind of close and then let go. It's pretty close to horizontal, not perfect. You get the idea. I can kind of push it down a little bit and hopefully get it to get as flat as I can get it. That's pretty flat. All right, now you can see the levitation happening. If I give it a nudge, it's resisting me, right? It's resisting as I try to turn it, but if I really work hard, I can get it to spin. And you can see because of the corners how frictionless the whole process is happening. You can see it kind of back and forth, back and forth. That's because the flux is pinning and it's kind of like overcoming the flux pinning in place there. All right, now what I have is a donut magnet, and what I'll do, I can feel the repulsion happening as I bring it down on top, right? But what I'll do is force the field lines into the superconductor, force it to be pinned, and when I feel like I've got it, I can lift the whole thing up, and it will be suspended underneath the magnet here. So now what we have is a track made of magnets, and I bet you can guess what's going to happen next. If we're careful, we should be able to levitate this thing pretty far above this track of magnets. Let me get it nice and cold, right above the track, and let go. Oh, look at that. You can just push it all the way around in a circle. And check this out. You can get it to pin in different orientations. As I move it, you know, I can go down closer to the track. I can try to pull it up from the track. And what we can do is we can pin it in place, flip the track upside down, and we can actually have it suspended underneath the track. Now, if there's one thing you've noticed during this whole thing is that you can see I'm constantly adding liquid nitrogen to get it to have these effects. All of these effects are only present below what we call the critical temperature of the superconductor. Now what I'd like to do, since you've seen some of the amazing things superconductors can do for us, I'd like to talk to you a little bit about when we first discovered superconductors, what we know about them, how they sort of behave, and the current theories as to how superconductors work. All right, so now that we've done the practical, I'd want to dive into the theory and the history a little bit more. Superconductivity, you don't think it impacts your daily life, but it actually does. And so we try to understand it so that we can build better and better higher temperature superconductors that can work in everyday circumstances. So for instance, when you go to the hospital and you get an MRI done, scan your body, the machine that you go into uses superconductors. I want to say that again, because a lot of people think this is just some lab rat doing some stuff. No, it's able to, we are able to build machines like MRI scanners for your well-being, because there's a superconducting magnet inside of it that's carrying a very high current, producing a very high magnetic field. Because superconductors don't have any electrical resistance, we can build electromagnets out of them that generate very high magnetic fields. And of course, someone discovered how you can scan a body with that technology. There's a whole lesson there for another day on how it works, but without superconductors, they wouldn't function. All right, and then we have our particle colliders, which we're learning about the nature of matter and so on. And then of course the holy grail is we'd like to make a superconductor work at room temperature. All of these superconductors have to be cooled down, and so we want to make one that can be used at room temperature. As you know, we transport electricity across the world through wires, but we lose energy in the electricity, power dissipation, because of frictions from the electrons traveling through copper wires. What if we could make a superconductor wire that could travel across the world with no losses? Then we would reclaim a lot of energy losses due to electrical transportation of electricity. So superconductors, if we ever find one that can be cheaply made at high temperature and work at high temperature, it would be one of the biggest discoveries in the history of humankind for our energy and power needs. All right, so let's go through the history a little bit and tell you where we're at today, and then we'll close with a theory of how we sort of envision superconductors working. I'm going to say in the beginning, we don't have a fully baked theory for how these things work. We're discovering new superconductors without really understanding the core fundamental principle behind which that they operate. We have ideas, I'm going to share them with you today, but the high temperature superconductors that we have, called type 2 superconductors, we don't know exactly how they work. There's a lot of things in science we don't know yet. We're trying to find the answers. So one of you guys may be the one to figure out the answers. All right, the first superconductor discovered was actually the element mercury. It's not even a chemical compound, just a pure element mercury. So, you know, mercury is a liquid at room temperature. I say you can hold it in your hand, but you shouldn't, because it's very bad for you. Okay, it's a neurological agent. It's very, very bad for you. Never hold mercury. All right, but I'm just saying, if you were to hold it in your hand, it's liquid, right? If you cool mercury down, it turns out very, very, very cold temperatures, it loses electrical resistance. We're going to talk about that in a lot of detail in just a second. But I want to emphasize to you that when I say it loses electrical resistance, I don't mean that superconductors just have low resistance, right? I mean it has zero resistance, like literally zero. There have been experiments that have been done where you take a superconductor, you run an electric current through it. Any wire, if you try to run electric current through it, it's going to get a little warm because it's of the internal collisions of the electrons, and the current will be dissipated, right? So you lose the energy to heat, and of course you have to keep the battery connected in order to circulate the current. But in a superconductor, you can actually connect a battery and make a superconducting loop, and then you can disconnect the battery and bridge the circuit, and you can keep the electricity flowing in a loop without any battery. In fact, this experiment's been done many times, and they can take that circulating loop of current, put it in a warehouse. You got to keep it cold. You got to keep liquid nitrogen on it or something even colder than that. But you can pull it out 20 or 30 years later, and this has been done, and the electricity is still flowing around in that loop, right? It's not a theoretical thing. It's actually still, I mean, they have these things in warehouses and they still check them every year, and as far as we can tell, there's no measurable degradation to the electricity flowing in a superconductor. It literally is zero. It's a quantum mechanical effect. All right, now we know that electrical resistance is has to do with the electrons colliding as they travel through the substance, right? And so what we can do is we can plot the resistance as a function of temperature. So we can call this, I'll put R for resistance. Really, in physics you call it resistivity, and that's when you take the resistance and you control for the diameter of the wire and all this stuff. But for now, let's just call it resistance. When you shove electrons through a wire, those electrons jump from atom to atom, and as they jump from atom to atom, they collide with other electrons. They collide with other electrons, other atoms that are in the way, and when they do those collisions, they lose a little energy. So we can use a battery to keep the electrons moving, but there's constant collisions. That shows up in resistance. In any electric circuit, we say there's resistance. We try to push the current. We can overcome the resistance with a battery or some other voltage source, but there's an inherent resistance into pushing electrons through a wire because of collisions. Remember, even at room temperature, we're nice and comfortable, but atoms are jiggling around violently at room temperature because, you know, absolute zero, we're very far away from absolute zero. You know, we're almost 300 degrees Kelvin, or you don't really say the word degree, 300 Kelvin, right, above absolute zero. I'm rounding a little bit here, but you get the idea. We're very far from absolute zero. So as you get colder and colder, the thermal motion of everything starts to slow down. Now, you can never get to absolute zero, but theoretically, as you approach it, you start to slow down more and more and more. So as we measure the resistance of something, right, over here at a high temperature, let's say this is like room temperature, it's about 300 Kelvin or so, 293 Kelvin, right? As we cool down, I'm going from the right to the left because these are high temperatures. Like you could say this is 300 Kelvin, right? And as we cool it down to like 200 Kelvin, 100 Kelvin, here's like 0 Kelvin over here, we expect the resistance to go down, right? We expect it to go down. But in the early 1900s, these experiments were being done, and we really didn't know what the resistance would do when you got really, really cold, right? There's a couple of, you know, kind of things you might wonder about. Would the resistance just keep on going down? And eventually it would, at 0 Kelvin or close to 0 Kelvin, we would have some minimal resistance. Would the resistance kind of get and start to bend over more and maybe land at, you know, maybe not zero resistance, but some lower value of resistance kind of as we get to absolute zero, close to absolute zero? Or would some other effect kick in and somehow the resistance goes up as we get colder and colder and colder? Most people thought that the resistance would just go down, 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 and as you get to ultra cold temperatures, you just have some very low resistance, right? But actually what happened is the following. When you cool a superconductor in certain materials, mercury for instance, we'll call this mercury. This is the symbol on the periodic table for mercury. As you get down colder and colder and colder, the resistance gets lower and lower and lower, and eventually it departs, and then it just goes straight down, right? And it goes all the way down so that the resistance is actually zero at a temperature above 0 Kelvin. This is not okay. This is 0 Kelvin, right? So for mercury, this temperature is about 4.2 Kelvin. This is really, really, really cold. Mercury was the first superconductor discovered, and it has what we call a critical temperature at 4.2 Kelvin. Now, I want to stop for a second, and I want to transition our thoughts away from superconductors. Let's talk about water. We know all about phase transitions. there are certain temperatures that water behaves differently. If you get it down to 0 Celsius, it changes from this liquid into a solid hard substance we call ice. And if you melt it and it goes to water, then it can flow. If you take the water and you heat it up and heat it up and heat it up to about 100 Celsius, then it changes phase again from liquid to vapor. And it can float away, and it has totally different properties. So ice and liquid water and gaseous vapor water have completely different characteristics. You know, the ice is solid and hard, the liquid flows easily, and the vapor can expand to fill the room. Completely different situations. We have connected all those together through the theory of matter, and we know why those phase changes happen. As we talk through the superconductors, I really want you to start to think about the difference in the way the material behaves as a phase transition. I'm going to call it a quantum phase transition. That's what people typically refer it to. But just keep in mind that all phase transitions of any matter is quantum, because all matter is made of things that are quantum things. These molecules, they're all quantum objects, right? But the behavior of superconductors wasn't noticed because it was impossible, or we didn't have the technology to make temperatures that cold or to cool things down that far until the year 1911 was when it was discovered. So it turns out if you take mercury and you make it very, very cold, eventually it gets hard and it's to a solid. It turns into solid mercury. And then if you keep making it colder and colder and colder and colder and colder, the resistance goes down, 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 but eventually at around 4.2 Kelvin, the resistance disappears completely. All right, 0 resistance. Now, mercury is what we call a type 1 superconductor. I'm going to differentiate that with a type 2 superconductor a little later, but I need to get a little farther in the lesson. Essentially, there are two broad classes. The type 1s really only work at very low temperatures. This is just a few degrees above absolute zero, very, very cold, and you need liquid helium to actually even do the experiment. Liquid helium is very expensive. It's very expensive to make very, very cold, to take the heat out of something enough to make liquid helium. So it's a very big deal if we can make a superconductor work at a higher and higher critical temperature. All right, so I'm going to go through a couple of discoveries. So people did lots of discoveries. I'm skipping over a lot. There are actually quite a few elements on the periodic table just by themselves. They superconduct at very low temperatures. 6 Kelvin, 8 Kelvin, 10 Kelvin. A lot of experiments were done trying to find materials that work at a higher and higher temperature. Finally, a breakthrough happened, and I'm skipping a lot of history, but a breakthrough happened in 1986. So in 1986, a compound was discovered. They call it LBCO. This is lanthanum, barium, copper oxide. This is not carbon, okay? And this is not the actual chemical formula. The subscripts, I'm not writing the subscripts here, but it's called LBCO. Lanthanum, barium, copper oxide. You're going to find out that the copper oxide family, those are the superconductors I worked on for 3 or 4 years. Copper oxide family is extremely prolific with lots of different superconductors coming out of that family. The first one was this, and this one here. And the critical temperature here, was 35 Kelvin. All right, so not that cold, but definitely warmer, but you still need a liquid helium to cool it to this temperature, right? Because liquid nitrogen, which is what I was using in the demo, is at 77 Kelvin. I'm going to write that down. I'm going to write that down, I guess, over here. So Ln2, this is liquid nitrogen, is about 77 Kelvin. Liquid nitrogen is actually really cheap, right? It's still way colder than room temperature. If you think in Celsius, that's about -195 or so Celsius. So that's very, very cold, but it's very cheap to make liquid nitrogen compared to liquid helium. So this, you still need liquid helium to to operate, or to bring it down below its critical temperature and see the superconducting effects. All right, but also in the year 1986, 1987, there was a lot of stuff going on. They replaced the lanthanum element here with yttrium on the periodic table. Yttrium, barium, copper oxide. My professor actually was involved in this heavily in 1986, and Dr. Paul Chu is fairly famous for this high temperature superconductor renaissance. The temperature of this guy was around 90 Kelvin, the critical temperature. That means that since liquid nitrogen is at 77 Kelvin, but this yttrium, barium, copper oxide works above 77 Kelvin, that means that we can cool it down with liquid nitrogen and bring it below its critical temperature very, very cheaply, because liquid nitrogen is cheap. I know that it looks so weird with the smoke and all that, but it's much cheaper than liquid helium. I've done experiments with liquid helium, and you need a much more sophisticated setup because it's just so hard to keep helium cold at that temperature. You need a super, super industrial vacuum jacket. Very difficult to do it. Gigantic machines just to keep a tiny amount of helium cold enough to do anything with it. Whereas liquid nitrogen, I can put it in a thermos and it'll be okay for an hour or so before it boils away. All right, so that was a big deal. That was before my time. I was not in college in 1986, but that's when the renaissance for what we call high temperature superconductors. When you see someone refer to high temperature superconductors, it generally means a superconductor that works with liquid nitrogen, anything above 77 Kelvin, right? Now, in 1993, which is actually when I started university, there was a family of compounds that was discovered, and these are what I worked on. So in 1993, there was a family of it's a whole family, actually, of compounds. And this one is the following. It's mercury, barium, calcium, copper, oxide. And there's a different number of oxygens depending on how you make it. And also, so we called this mercury 1, 2, 2, 3. That's what we called it. But actually, there's a whole family. You can have mercury 1, 2, 1, 2. So you can have a 1 for the calcium and a 1 for the copper. It's also superconducting. The temperature of this guy is, you ready for it? A whopping 138 Kelvin, right? Much, much higher than this one, which was, almost 10 years earlier, right? And I'm going to mention it a whole lot more, but these copper oxide superconductors, the interesting thing about them is if you apply pressure to them while they are cold, like literally if you take the puck, put it in a vise and squeeze it while it's cold, the application of pressure actually increases the critical temperature. Physically forcing the atoms in the lattice closer together actually increases the critical temperature. And we're going to find out in just a second, all the way up to very close to room temperatures we actually have already discovered. I'll show you in just a minute as we write it down. All right, so mercury, barium, calcium, copper oxide. Right? Now, before I go on, since I spent a few years of my life making these things, I'll briefly explain how they're made. So mercury oxide is a powder. These are all going to be oxides. You buy them from the chemical company. Mercury oxide, barium oxide, calcium oxide, copper oxide. You don't need any oxygen because the oxygen's already in the other compound. So 4 compounds, they're all powders. And what you do is you mix them together in the proper proportions, you grind them together to get maximum contact of the different atoms, and then you press them into a pellet, literally into a puck. You do that in a vise and you apply pressure and you put it in a puck. You take that puck and you put it inside of a glass or a quartz tube, which is sealed, and you put that inside of an oven or a furnace and you bake it. So it's like an easy bake oven. You put it in there at about 1,000 degrees for 5 or 6 hours. It depends. We try 6 hours, 10 hours, 12 hours. That's all the experiments we were doing back in the 90s. How much do you put in there? What temperature? How long? All that stuff. Out after 6 or 7 hours, the puck that you have, which was gray, is now black. And when you measure its resistance at room temperature, it's not a good conductor at all. But if you cool it down, it becomes a superconductor. Okay, and like I said, this is a whole family of superconductors here as well. All right, now I moved on from superconductivity, and so lots of research has happened between now and then. I'm not really up on all the latest, but I'll tell you the highlights. In 2019, I was certainly not involved in any of this stuff. A compound called lanthanum hydride had a very high critical temperature. So I'll write it down. I guess I'll write it down here. So in 2019, lanthanum hydride. So lanthanum on the periodic table in 10 hydrogen atoms has a critical temperature of 250 Kelvin. Look at this. Room temperature is just under 300 Kelvin. So 250 Kelvin is really close to room temperature. But there is a catch. The only way they were able to get 250 Kelvin is by applying pressure to this thing. And not just a little pressure, 170 gigapascals. Now, you might say, who cares? What's a Pascal? Well, I'll tell you. I'll just go up here and I'll tell you that 1 atmosphere, so what you feel right now, is somewhere on the order of about 100 kilopascals. So what you feel right now on your skin from atmospheric pressure is about 100 kilopascals. So this isn't kilopascals, this is billions of pascals. So this is not just a little bit of pressure, this is an enormous amount of pressure. And the way you apply this pressure, actually, you don't just use a vise, you have to have a diamond. Diamond is the only material that can withstand the pressure. You have a diamond anvil with sharpened points, and then you put the superconductor between it, and you apply this incredible amount of pressure while you cool it down. And it turns out that they can get a superconducting critical temperature up to 250 Kelvin, right? And then in 2020, which was at the time of this recording, literally just 2.5, 3 years ago, I don't actually have the entire formula here, but it was a compound with hydrogen, carbon, so not calcium, carbon, and sulfur. One of these days I'll look it up and see what it actually is. Has a critical temperature on the order of 288 Kelvin at 270 gigapascals. Now 270 gigapascals, I can't even fathom it, okay? This is like the center of Jupiter kind of pressures, all right? So the point is, you might say, well, this isn't practical. Who cares if they made a room temperature superconductor at so many gigapascals? This is the way science often is. See, when this superconductivity was first discovered, scientists really didn't think it could work at all above 20 or 30 Kelvin. Just theoretically, it just wouldn't, because we didn't understand how it worked, and their best theories basically just thought that the process wouldn't even occur above a certain temperature. I mean, after all, ice and steam, you know, they have very fixed phase transitions, right? So maybe this only works at certain temperatures and that's it. Maybe getting room temperature superconductors, impossible. Well, what this proves is that we have different compounds that operate very close to room temperature, but we have to apply a lot of pressure. Even though we have to apply a lot of pressure, and so it's not practical to build a wire out of it right now, what it tells you is that theoretically it's possible, because not only is it theory, it's demonstrated that superconductivity can exist at a high temperature, at a room temperature. Even though the pressure has to be high, it gives you an existence proof. It shows you, hey, this does happen. Just like the first superconductors happened at 4.2 Kelvin. Now we have them operating way higher than that. This tells you that there is such a thing called a superconductor. And this tells you that it's possible to get that critical temperature up close to room temperature. All we have to do is understand the theory enough to know why the pressure influences it in the way that it does. Then maybe we can engineer a compound that works without the pressure. So it's one thing at a time, right? First you discover penicillin as an antibiotic. And you're like, wow, antibiotics exist. And then you go research and we now have whole families of antibiotics. So it's my firm belief that, hopefully in my lifetime, but definitely in yours, that we will have superconductors that are room temperature and that function at room temperature. All right, so let's go in a little more detail and talk about how this works a little bit more. So we have this concept of zero resistance. And I already drew a graph on the board, but I want to draw another one because I want to show you how we measure these things. So this is the temperature in Kelvin, and this is the resistivity or the resistance, right? And as I said, here you have room temperature is actually, it's 300 Kelvin, but it's actually 293 Kelvin. I was just rounding there. So this is room temp. This is a nice, comfortable day. The resistance of most substances is up here, and as you cool it down, then it just drops right off a cliff and goes down at some critical temperature, which we call Tc. What we want to do is move this Tc way up here. So the critical temperature is like somewhere near room temperature. That's what we want. So it's always superconducting, even without any coolant at all. That's what we want. Now, just because I've done it a few times, I want to share with you, how do we measure this? How do we actually measure the critical temperature? What you do is you take your superconductor, which is, like, I'm drawing a rectangle, but it could be a puck in a circle. And what you do is you make 4 contacts on the surface of the superconductor. So there's one contact, there's another one, here's another one right here, and here is another one right here. And in order to measure the resistance, what you have to do is you have to run an electric current through it, and you have to measure the voltage that's occurring across it. So what you do is you hook the outer ones to a current source. So I'm going to put I right here. And it's, I guess I'll put little dots right here. So it's connected right there. And so the current kind of goes around through here, through the superconductor, and then back around. So there's this electric current circulating there. And then what you do is, at the same time you're measuring this electric current, or you're sending this electric current, you connect a voltmeter across here. So I'm going to put volt, but this is a meter here. So this is sending electric current through, and this is measuring the voltage across the innermost pads. Now, why do we have different pads here? Well, if I take a regular voltmeter, like from the hardware store, and just connect it, what the voltmeter is doing is it's sending current through, and it's measuring the voltage from the same probe tips. The problem is, if you touch a superconductor, with the same probe tips, if you don't separate them like this, what's going to happen is there's a contact resistance from where the probe tip touches the superconductor. So if you measure the voltage at the same place the probe tips are touching, you're going to measure the contact resistance. Since the superconductor gets all the way to 0, then you don't want to measure any other resistance anywhere other than the superconductor. So you have to separate the current going in and the measurement of the voltage. Now we know from Ohm's law, from electronics, V is equal to IR, right? The voltage across anything is equal to the current flowing times the resistance. And so you can calculate the resistance as V over I. So what you do is you send current through here, and so you know what the current is, and you measure the voltage across this little interior piece right here. And as the voltage approaches 0 or goes to 0, right? As the voltage goes to 0, then the resistance will go to 0 also, because the numerator will go to 0. And so you plot this the whole time. You're basically sending current through, measuring the voltage, and as you slowly cool it down, the voltage is going to go down, 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 which means the resistance is going down, 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 down. Eventually, after it's superconducting, even though you're sending a current through, there's no voltage drop across it. If you've done anything with circuits, you know that if you have a perfect conductor, which you never can have outside of a superconductor, then there's no voltage drop. But across a superconductor, there really is no voltage drop, because you don't have to supply any voltage to continue the current flowing. It's just going to flow for free, for lack of a better word. All right, and one last thing I'll say is that in order to connect these things, because I had to do it for so many years, you get under a microscope, and you get this indium metal. It's a metal on the periodic table called indium. It's quite expensive, but it spreads like peanut butter. It's kind of a soft metal at room temperature, and literally under a microscope with tweezers, you spread the indium metal on the superconductor and you connect your wire. You put a platinum wire here, and 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 you spread this indium metal and you spread it on top of this platinum wire. So at the end of the day, under the microscope, you're looking at 4 contact pads, 4 wires coming out, and you connect them to a measurement device, and then you slowly cool it down by slowly lowering it in liquid nitrogen. And every time you drop it down closer and closer to the liquid nitrogen, you measure this resistance, and then you get a graph that looks just like this. Maybe one day I'll do that. It would require a lot of work, so I'm not sure I have the setup here to do it. It would be fun to do it, but that's how it is done. All right, 0 resistance, literally exactly 0 resistance. Why do all of these levitation effects happen? Okay, now this is when it gets into theory, and I can describe to you what the current theories are, but just know that it's all quantum mechanical effect, and we don't know exactly how these type 2 superconductors work. Remember, type 1 are the superconductors that only work at very low temps. Type 2 are all of the newer superconductors that work at the high temps, right? So we know from electricity and magnetism that magnetism and electricity kind of go together like peanut butter and jelly. I'll say that again. Magnetism and electricity go together like peanut butter and jelly. They're really manifestations of sort of the same thing, which we call the electromagnetic field. So because of that, magnetism can induce or produce electricity, and electricity, flowing electrons, also produce their own magnetic field, right? So how do we use that? We use it every day in a motor. When you have a motor and you run an electric current through a motor and it spins, what's happening is you're running an electric current, there's a magnet in there, and so there's a force that's exerted, a magnetic force, and so the thing turns. If you run it backwards and you get water or steam to turn a turbine or a generator, then you have the same setup. You have magnets and you have wire, and you're turning the coil of wire in the magnetic field and you're generating electricity. So what happens if you have a perfect conductor? And I mean a literal perfect conductor. If this is your superconducting puck right here, and it's cooled down below its critical temperature, and then right above it, I bring up a magnet here, so like north and south pole of a magnet, and I begin to lower it down. Well, we draw these field lines around the magnet like this. And by the way, these field lines, there's a lot of debate on what you want to believe, right? Are they real? Are there real field lines there? Well, not really sure. They're a good calculational tool. They're a good model of the universe, right? They're a good model of the universe to explain how things interact. Are there really invisible lines? I mean, no, not really. Maybe. Depends on how you want to think about how real things really are. If it exists in a way that helps us predict what's going to happen next, if it gives us a self-contained way of predicting things, then they might as well be real. But are there really invisible lines? No, not really. It's just that these things behave in a certain way that are nicely predicted if we envision an invisible field with this geometry around it. Okay, so that's a little bit into philosophy, because what is real, what is not real. But magnetic fields, electric fields, they exist right on the edge of like, if you believe they're real or not, just depends on your view of reality, and if you think that something is real, if it has predictive power or not. All right. So that's my little spiel there. But anyway, here's a magnetic field. If you drop this thing down into the superconductor where the field lines attempt to penetrate the superconductor, right, what's going to happen? It's a perfect conductor. We know from Maxwell's equations that govern electricity and magnetism that anytime you have a changing magnetic field in a loop of wire, it generates an electric current. But this is not just a loop of wire. It's a solid conductor of perfect wire. Perfect. So you can think inside of here as like there's a bunch of current loops which are all like infinitely close together, like it makes a whole gigantic puck. As soon as you bring this thing close, like when I was dropping the magnets, the magnetic field starts to try to penetrate this conductor. But as soon as the first magnetic field line attempts to make contact with this conductor, immediately at that moment, this magnetic field induces an electric current to flow in the conductor. We call it an eddy current. Eddy current is a nice little term that just means that these little currents are existing as little miniature circles somewhere in the conductor. I don't actually know if it's oriented this way. I haven't done the right-hand rule to figure it out, but as you bring this magnetic field down, some current is going to be generated somewhere in this puck. And that current in a superconductor will always be generated in such a way that this current produces its own magnetic field. Remember, electric currents also produce their own magnetic field. But anyway, the magnetic field from these eddy currents will be produced in such a way as to try to cancel the magnetic field approaching. And it has to do that, by the way, because if it didn't, then you have a larger and larger magnetic field. Because it's a superconductor and it's perfect, you would have a magnetic field that would grow forever, and with infinite, because magnetic fields store energy, you would have a free energy machine, and that can't happen. So in the real world, when you bring this thing down, the magnetic field begins to cut through this conductor. It generates an electric current, which produces its own magnetic field, which tends to cancel this magnetic field approaching, so that the end result is we say superconductors do not allow any magnetic fields inside of them. But it's not because there's a person standing at the door slapping away the magnetic field. It's not because they care. It's just because the eddy currents that are generated in the surface of the puck, the first minute presence of magnetic field immediately generates a counter-magnetic field that cancels the one approaching. So no magnetic fields can exist inside of a superconductor. So you might say, what basically that looks like is as soon as the field approaches, instead of going through, like if this were just, plastic or something, the magnetic field would just go right through. But in a superconductor, the magnetic fields literally go around. And I'm not drawing any arrows. Of course, magnetic fields have arrows, but you get the idea. All right, now, I mentioned many times as we did the experiments, I told you, I bounced it off and I showed you how it tends to repel magnets. But then I showed you if you kind of overcome the repulsion, that's called the Meissner effect, when it tends to expel magnetic fields due to these eddy currents that are generated. If you kind of physically push it in there and overcome that resistance, then for type 2 superconductors, only type 2 superconductors, you can force the magnetic flux to penetrate the superconductor. And then once it's inside, it's actually frozen in place. It's locked in place. So I'd like to talk a little bit about that. We don't have all the theory here, all right? So I want you to know that what I'm telling you are sort of like the current theories, but it's definitely not, not written in stone, because these theories superconductors are the cutting edge of science. So we don't actually know exactly how they work. But the theory is that, let me see if I have enough room on this board. Yeah. In a type 1 superconductor, this is how it would behave. So type 1. Type 1 superconductor. It would allow absolutely no magnetic field inside of the material, and it would be purely repulsive effect, no flux pinning, right? But in a type 2 superconductor, which is the mercury, barium, calcium, copper oxide, or the yttrium, barium, copper oxide, those and all the other newer ones, those are all type 2 superconductors. So there's basically a lattice of the bariums, the yttriums, and all the things that is made of the superconductor in a regular lattice, right? But that lattice is not perfect. In other words, if the material is mercury, barium, calcium, copper oxide in these proportions with the subscripts here, then maybe once I pressed it in there and I baked it, then the lattice maybe at this location, right at this point, isn't perfect. Maybe instead of 2 bariums at this spot it's supposed to have, it only has 1, or it has 3 of them. Or instead of, enough oxygens over here, it has 1 less oxygen. In some sort, throughout the lattice of the structure, it's not exactly perfect in all locations. So the local superconducting effect in certain little zones in these type 2 superconductors isn't really perfect throughout the whole thing. And the idea is when we force the magnet in there, if it finds one of these local defects, then the flux and the magnetic field can penetrate locally in that region. We call that a flux tube, believe it or not. Right? So in that situation, what you might have, a little cartoon for it anyway, would be the following. Right? So I'll say type 2. Type 2. So what you have is you have the magnetic field for the most part being expelled, from the superconductor. But then, if there's a defect right here, then maybe what you have is, let me get to my picture so I can make sure I draw it the way I want to draw it. Then maybe right here, the flux can kind of penetrate right in this one little defect zone, something like this. Right? And right here, and then maybe there's another one right here where the flux can kind of like be concentrated and just make it through this one little zone, which is not really superconducting. In other words, the superconductor as a bulk object, the whole thing we say is superconducting, but really if there's imperfections in the lattice of the structure of this chemical compound, and it's not perfectly mercury 1, 2, 2, 3 at this location, then maybe right at this location, it's not exactly superconducting. So at that one location, a tiny bit of magnetic flux can make it all the way through to the other side, and any flux coming in, instead of going around, will be able to locally penetrate right here. But the thing is that once it's locally penetrating through to the other side right there, then if you try to move the magnet that's generating this left or right, notice how it was kind of like staying in place. We call it flux pinning, right? As you try to move it away from that flux tube, from that imperfection, as soon as you move it, then eddy currents are generated nearby, which tend to push it back to the imperfection. That's why it's pinned in place. That's why the levitation happens. We've all played with magnets. Everybody has. You love to repel magnets. It's just magical. But notice that it's very unstable. Magnetic fields can repel each other, but they're very unstable. That's because in two magnets, nothing is pinned. The magnets are repelling each other because of the interactions of the magnetic field, but it's almost like balancing a pencil on your finger. It's very unstable. In this situation, it's not so much that it's being repelled, it's that it's being trapped. The flux is being pinned in place, and that is why when I lift up, it tends to resist me lifting up. When I push one side, I can get it to reorient itself because the flux can be pinned in whatever location I release to through these specific sites, which are defects in the bulk superconductor. That is a theory. That may be proven wrong, but that is the current theory as of right now. Okay? So type 1 superconductor accepts absolutely no flux. It's just a repulsive effects. Type 2 superconductors operate at higher temperatures. They're more complex. They have a crystal lattice, and they can pin the flux, and magnetic levitation is what we have possible with high temperature superconductors. So if you want to build a train or you want to levitate a car, you would do it with a type 2 high temperature superconductor. All right, now before I forget, we've mentioned that superconductors have a critical temperature, right? And this critical temperature, right, we call it TC, critical temperature. Well, actually, there's some other things that you can do to superconductors to make them lose their superconductivity, right? That are different than just the temperature. It turns out that if you have a superconductor and it's in the superconducting state and you put too much electrical current to it, through it, then the superconductivity will stop. and that's called the critical current density. So I'm just going to say JC. J is the symbol in physics for current density. This is the critical current density. So I'll say current density. That's JC. So if you have a superconductor and you put 100,000 amps through it, it's going to immediately stop superconducting. Somehow, by putting too many electrons through the bulk material, it disrupts whatever is causing the superconductivity in the first place, and the thing will immediately transition back to the normal state and start to heat up, even though it's very cold, right? Secondly, or I guess I should say thirdly, I wish I wasn't running out of space, there is something else called a critical magnetic field. We call it BC. So this is the magnetic field. Right? Right now I'm putting these magnets, levitating them on top of a superconductor. Everybody's happy. But if I take a very, very strong magnet, very strong magnetic field, and I immerse the superconductor in a super, super strong magnetic field above some critical magnetic field strength, superconductivity turns off. So there's not just one thing that can turn off a superconductor. There's actually three things. There's probably other things too. But the three main things: if you make the temperature too high, the superconductivity stops. If you make the electrical current too high, the superconductivity stops. If you immerse it in a magnetic field that's too high, the superconductivity stops. All right. Now I'd like to close with the current theory as to how this actually happens, but I want to caution you a couple things. First, I want to caution you that this is just a theory, right? In years to come, someone will come up with a better theory, and that theory will model the situation better, and it will yield hopefully more discoveries. But this is the theory that we have right now. It was put forth a long time ago. Secondly, this theory only really applies to type 1 superconductors. It isn't really a good theory for type 2 superconductors because the flux pinning and the behavior of type 2 is actually, I'm leaving out a lot, it's significantly different than type 1 superconductors. But the thing is, we really want to make more type 2 superconductors that work at higher temps, so people are searching for a theory that explains it. And when I say theory, these theories are not just put forth like some people just throw in darts at a board. They have predictive power. So we don't just put forth theories and say, oh, it sounds great. We put it forth and we ask, does it predict anything? So the theory that I'm about to show you and share with you is called BCS theory, and it does have some predictive power, and it has predicted some superconductors which were then discovered. Okay? BCS stands for the names of the authors that put forth the theory there. Okay, let me give you the big picture, and then I'm going to have to dive in a little deeper. Resistance in a wire happens because when electrons flow through the wire, they're basically undergoing collisions the whole way through, right? But somehow, as we cool the temperature down of lots of different materials, then the resistance completely goes away. So somehow the interactions of the electrons with the other atoms and electrons that are in the material, it somehow disappears. It's more analogous to a phase change, like water to ice or ice to gas, or liquid water to gas or vapor. A phase change. This is called a quantum phase change, where the bulk properties of what an electron is inside the material behave differently. I want you to remember, as I talk to you, that you don't know what an electron is. Neither do I, neither does anybody. We have theories. In grade school, we talk about electrons being little balls that collide, right? They're not balls. In quantum mechanics, we describe the electron as a wave function. It's like a traveling wave. I know it sounds weird, but that's what the current theories are. And believe me, they must have wave-like properties because electron microscopes, which we use every day, kind of rely on electrons behaving as waves. So we know they have a wave character, right? And waves can interfere, and waves can add and subtract, and waves can do all kinds of things that waves can do. But we also know that electrons have a particle-like property. They collide, they bounce off of things, and waves don't seem to do that. So electrons, whatever they are, have characteristics of waves and particles, just like photons of light also have characteristics of waves and particles, right? But I'll give you the big picture. The big picture is that light is called a photon. It's a particle of light that has a wave-like character. And light is able, the photons of light are able to, if I had a bucket of photons, then they would all be able to coexist in the same quantum state. In other words, they would be able to have the same energy level. The photons could all be literally sitting on top of each other. Photons don't really collide and bounce off of each other. You know that. Take a flashlight, take another flashlight. Do you see anything bouncing? Do you see any photons bouncing off of photons? No, they bounce off of matter. they bounce off of air, they bounce off of mirrors, they bounce off of planets. But photons don't bounce off of photons. They can exist in the same place with the same color, with the same energy, no problem. That's how we make lasers. Laser is a very pure color light, and the reflection back and forth in the laser cavity makes a bunch of photons in the same quantum state, right? Now electrons are different. Electrons seem to bounce off of each other. They can collide, and so they can't exist. A bucket of electrons cannot exist in the same quantum state. They're fundamentally different. Electrons cannot all be together at the same energy in the same place, occupying the same space. If you try to take an electron, put it here, and you put another electron right on top, even if they weren't charged, because I know you're thinking, oh, they're repelling. Forget about that. They still cannot be in the same place because they are fundamentally different than photons, right? But I'll give you a hint, the punchline, and as we talk through it, I want you to remember this. This is important. In the superconducting state, the electrons that are flowing start to behave like photons. I'm going to say that again because that's really important. The electrons that are traveling through the superconductor, as a group, as a conglomerate, they start to behave kind of like photons. They undergo a phase transition, a quantum phase transition, where they stop acting like these individual balls that bounce off and can't exist in the same place and they can't be in the same energy, the electrons of every other atom we examine, and they start to transition to a different kind of entity where they can exist in the same place, and they can act as a group, and they can all be in the same energy. In this state, the electrons can move through the material without interacting with any other adjacent electrons because they're all, remember, the atoms are almost all electrons, right? The protons and the neutrons in the middle are there, but the atom is mostly completely empty space surrounded by a sea of electrons. So as an electron goes through, it's not going to interact with a nucleus, it's going to interact with other electrons, mostly. But if all the bulk electrons start behaving as one whole entity thing, then they're not interacting with each other, they're not bouncing off of each other, they're not colliding with each other. Now, if you start to warm this thing up and make it agitated and disrupt this quantum phase change, then suddenly they start to behave like regular electrons again, and they start colliding and resistance starts to happen. That, in words, is what is happening. But I want to draw some pictures so that we can go a little deeper together. And I find this fascinating. I hope this is, will be expanded upon to encompass the type 2 superconductors, but we'll have to see in the future. All of matter and all of energy, everything you've ever seen in your life, is really governed by one of two classes. We call them bosons and fermions. I promise it's got weird names, but these will be easy to understand. So you have something called a boson. These are all named after people, right? And you have fermion. These are classes. These are not particles, these are classes. So the example that I want you to think of for a boson is called a photon. Whoops, if I can spell photon right. I mean, it kind of sounds the same. Boson, photon, they sound the same, right? Fermion, the example I want you to think here is an electron. Fermion, electron. I mean, it doesn't really help as much, but you get the idea. Boson, photon, they sound the same. Fermion, electron. Now, there are other kinds of bosons. There are other kinds of fermions, but I don't want to talk about those because we'll spend all day. Let's just talk about photons. Let's just talk about electrons, okay? Now, here's the part where I have to start to get a little abstract. A photon has a characteristic. It has energy and position and all that stuff, but it also has something called spin. I'm going to talk about it in a second. And the spin is an integer. That's what makes it a boson. Anything that has a spin that's a whole number like this is called a boson, right? Now, anything that has a spin that's not a whole number, like an electron, has a spin of 1/2. Anything with a fermion which has some kind of fraction, doesn't have to be a half, but it has to be a fraction, it's called a fermion. Right? Now, I want to come back to what spin is in just a second. Please, I know you're thinking, what is that? Are they really spinning? Just hold it, because I promise I have all the same questions you do. So just kind of let me get through, right? We will come back, I promise you. I remember in 9th or 10th grade, I spent like weeks trying to understand what spin was, and then I realized nobody really knows what spin really is. So join the club if you don't understand what spin is. Nobody does. Not even the experts know what spin really is. All right, what this means is that in terms of photons, all photons can exist in same state, quantum state. What I mean by quantum state, they can have the same color, they can have the same intensity, they can have the same energy, and they can have the same position. right? This is what happens inside of a laser. We use this all the time. And this, it means if you draw like an energy level diagram where this is energy, then what it means is that some minimum energy right here, then what you can have is you can have a bunch of photons just hanging out at this low energy state. This is energy on this axis, some low energy, so whatever the color of the light is. Red light has a certain energy. They can all the photons can be inside the laser cavity with exactly the same wavelength of light, and they can all just be passing through each other. They don't interact with each other at all. They can exist in the same place. This is what photons are, right? We don't know why spin of one makes it do that, but it does. Sorry, if you want deeper explanations, I'm not going to be able to help you because nobody understands exactly why quantum mechanics behaves the way it does. But we do know that all of matter is either a boson or a fermion. Spin 1 means that they can all exist in the same state like this. Same location, same place, same quantum number, same everything. This is how we make lasers of exactly the same color, coherence, all the stuff that makes a laser what a laser is. Now, because I've led up to it, hopefully you should know a fermion doesn't behave in the same way. Can't share same quantum state. You may remember from chemistry something called the Pauli exclusion principle. When you learn about atoms, you learn, okay, here's a nucleus of an atom. Let me put an electron there. Okay, boop. Now there's an electron. You can think of it going around, but it's not really orbiting. But let's just think of it like going around for now. Now you take a second electron, you can put it in there. Boop, has to have a different quantum state. The quantum numbers have to be different for electrons to exist around an atom. You put a third electron, it can't be on top of the two that are there. It doesn't behave like photons. It has to be somewhere farther away with different quantum numbers than the ones that are lower. And if you put a fourth and a fifth and a sixth electron in place, they have to be different quantum states. That means the electrons have to get farther away with different quantum numbers. And that's why on the periodic table, when you look at iron with a lot of electrons, then the electrons are all, the outer ones are very far away. The inner ones are very, very close because electrons cannot be on top of each other with the same quantum states. Photons can. And the difference between them is basically what we call spin. I'm going to come back to it in just a second. Before I do that, let me draw a little picture of this. So in the nucleus, this is protons and neutrons in the nucleus, right? Here's an electron, right? And you learn in chemistry, right, that you can, in the same lowest orbital, you can have two electrons in the same lowest orbital. But in order for them to exist in the same lowest orbital, this one has to have like an up spin of 1/2, and this one has to have a down spin of 1/2. So when I told you that this thing has spin, there's one little nuance. Yes, spin is a number, but spin also has a direction. I'm going to talk more about spin in just a second. But up spin of 1/2 is different than down spin of 1/2. So two electrons can exist in the same orbital as long as one has up spin and one has down spin of a 1/2. But you can't put a third electron in that same orbit with those because electrons can only have an up or a down of 1/2. And so if you put another one here, it can't have a different quantum state. So it cannot exist in that lowest orbital there. We call it the 1s orbital. Energy level 1. S is the shape of the orbital. You'll learn about all this stuff in chemistry and quantum physics and things like this, right? If you put a third electron in place, it just can't be here. It has to be farther away in a farther distance from the nucleus. Again, different quantum numbers as you start piling more electrons in place. It's because of the difference between electrons and photons, because of the class of the particles there. Now, what is spin? I'm going to give you the punchline. Nobody knows. Nobody knows, all right? But what we do know is that electrons have what we call angular momentum. You learn in physics about something called angular momentum. If you take anything and spin it in a circle, like a merry-go-round, a child, just fling something around on a string, anything rotating has an angular momentum. And we know that electrons have angular momentum, right? We know this. Why? Because moving charges generate magnetic fields. If I take a coil of wire, literally, you can do this experiment. If you run an electric current through a coil of wire, you ever build an electromagnet and you put the nail and you wind the wire through it, the electrons are going through that wire, then they generate a magnetic field and they magnetize, they all add up and they magnetize that nail, right? That's an electromagnet. We can build these things. We know they happen. But we know that if you take a single electron, just one electron, I'll just put a right here. Thing is called an electron. It's got a negative charge. Just one electron. There's no atom, there's no wire, there's no nothing. Just one electron in an experiment. And you very carefully measure. That electron, in addition to having a negative charge, it also has a very small magnetic field. Let me say that again. The electron, we learn in grade school, they have negative charges, right? And so like charges repel, electrons repel. But also what you don't really learn in grade school is that electrons have what we call a magnetic moment. They have their own little magnetic field. And in terms of our framework of physics, the only way it can really have a magnetic field is if it were a tiny little coil of wire rotating, because we know that coils of wire generate a magnetic field. So if you take a single electron and you could rotate it, or if you take a single electron and just make it go in a circle, it should make a magnetic field. If you make the circle smaller and smaller and smaller, so it's not really making a circle anymore, it's just a single kind of like entity rotating, then it would have angular momentum, and it would also have a very small magnetic field, and electrons have a small magnetic field. We know this to be true. And the magnetic field can be oriented in one of two directions, corresponding to what we call spin. We say that the electron behaves as if it is spinning. Now, we know it's not spinning, right? We know it's not a ball. We know that all of these things, photons, electrons, quarks, all of it, they're quantum wave functions. So they're not little balls that spin. But whatever they are, they have a wave-like character, and they also have some sort of quality to us that to us looks like angular momentum. It looks like a spin. You can think of it as a spinning ball. So instead of, when you see spin, I want you to not think, oh, this thing is spinning. I want you to think, it has angular momentum, and that means it has a magnetic field. We don't know if it's spinning, or if the wave function is different than how we have it modeled, or exactly where the spin comes from, but it behaves as if it were a tiny, tiny, tiny particle spinning. And the electron has a magnitude of a spin that has to be some fraction, and that fraction is 1/2. All fermions have spins that are fractions, and the electron is a type of fermion that has a spin of 1/2. Now the photon has a spin of a whole number 1. And why, you say, why 1/2, why 1? You're starting to ask questions nobody knows the answers to. I shouldn't say nobody, but very famous people. Richard Feynman said, I think I can safely say that nobody understands quantum mechanics. If Richard Feynman doesn't understand it, nobody understands it. This is because when you start asking deeper questions, I could keep going. Well, why does it spin? I don't know. Nobody knows. Why? At some point, you have to get to a point where I don't want to say stop asking why, because I always want us to ask. But you have to accept that some things are just the way they are, and we have no capability currently of probing into some of those questions until we discover maybe other aspects of the universe. Maybe they're spinning because they're all connected to another universe somehow. Maybe all the universes are connected together, and the things that we see as spin is like their connection to another universe. I'm just making this up. I don't believe that. I'm just saying it could be related to something that we have yet to even discover. That's why it doesn't make a lot of sense to us. But I need you to know that a photon has a spin. It looks like a particle that is rotating with a spin of 1, and a whole number 1, and a fermion has a spin of 1/2, and because the spins are different, photons can all exist in the same quantum state, and electrons cannot. That's very important. All right, so now we have this information, we're able to finally understand the BCS theory of how superconductors work. All right, first, let's talk about a normal conductor. Normal conductor, so what we'll do is we'll draw a wire, right? And this is a cartoon, right? It's obviously a lot more complicated than this, but inside of this wire are nuclei, which I'm calling positives. Right now, the nucleus really of an atom has protons and neutrons. And so I'm considering the entire nucleus to be in these little balls. So the charge of the nucleus doesn't matter. I'm just putting them there, and just so you know, they're protons and neutrons in every one of these positive spaces. In a wire like a copper wire, there are electrons bound, but the outermost electrons are very weakly bound to the atom. They're very easy to get them to move. That's why they're good conductors. Like an insulator, like plastic or something, the electrons are very tightly bound, and so they can't move and jump between atoms very easily, so they don't conduct electricity very well. But in this case, they do. So if I had an electron, let's say right here, this is an electron, and I put a voltage across this wire to try to push this electron, right? Then this electron's going to go here. Oh, it's going to crash into this thing. And maybe there's an electron here as well. And then it's going to crash down here. They're going to crash up there into something. I'm not drawing all the other electrons that are here. There are electrons everywhere in here. It's a sea of electrons. And these positive charges and also these negative electrons, they're jiggling everywhere at room temperature. Everything's violently moving everywhere at room temperature. And so these things are scattered everywhere, mostly off of other electrons that are in this. But as a group, even though they're bouncing off of each other, as a group, they're still kind of making their way over this direction. And that's what we call electric current flow. But there's a lot of losses because every time it collides with another electron or something else in the way, it loses a little energy. Now we have a battery connected, which is always putting energy in and fresh electrons, and so the process can continue, but we're losing energy. We see that in an electric circuit as heat. The wire will begin to heat up. The toaster, if you think of your toaster oven, you put electricity is going through it, it gets very, very red hot, or a light bulb, getting it red hot, that's what we call ohmic losses, power loss due to collisions, due to frictional heating there as the electrons flow through, right? But the electrons are losing energy as they propagate through because of this collision process. Now, the theory of superconductors goes like this. So here we have a superconductor, right? Superconductor, right? So I need to draw kind of two different pictures, I think, to have it make sense. I'm going to draw one on top, and then I'm going to draw another one, I think, right down below. Again, you have to use your imagination. These are cartoons, right? This is obviously not real. But in the superconducting state, the nuclei of the atoms that are in there, they're not jiggling so much. You cool everything down, the violent motion of everything, they are moving a little bit. But as you get colder and colder and colder, these things are in the lattice structure in a little more of an organized way and not jiggling around so much. So they're more or less like this, right? And what happens is then if you send an electron in, like right between them, let's say, then what's going to happen is because these things are not moving so much and any other electrons in the way are not having as much thermal energy, then there's not as many collisions, right? And so the electron has a little more of a clear path. Now this does not explain zero resistance, but I'm just kind of setting it up for you here. Now I need to draw another situation. As this electron makes its way through, then what's going to happen is something like this. Let me draw it. These little atoms are going to be a little closer together, like this. Let me draw it. I sent an electron in from the left. Here's another electron coming in. The one that I already sent in is like maybe, let's say, right here. You see, when it gets to the center here, opposites attract. And this electron is sort of attracting the adjacent copper nuclei a little bit closer to itself. And because of that, there's a little bit of a higher density of if you look at this as draw a boundary around it, whereas before you had a neutral conductor, because they're physically pulled a little bit closer to the electron and because there's not as much thermal motion to kind of swamp everything, then from the outside, it looks like there's kind of a net positive charge here because these adjacent whatever material is, superconducting nuclei, are getting a little bit closer to the charge that I just sent through. So that means that this one, when it goes and starts to enter in, it's going to sort of see this negative charge, but it's also going to see an overall positive charge over here, and this negative charge will be weakly attracted to this net positive charge over here. I'm going to say that one more time because that is really the core of the theory. Because the thermal agitation is stopped, in some materials the electron can attract nearby positive nuclei. Remember, the electrons are more or less unbound. I mean, they're not really totally unbound, but they're very, very loosely bound. So mostly you have the positive nuclei left behind, and they're attracted, making an overall positive region. The incoming electron, the next one I send in, sees this and it's sort of attracted to it. So as these two electrons travel through the lattice, these two electrons begin to behave like a bound pair. I'm going to say that again. It's important. The two electrons begin to behave as a unit, because the first electron brings in some atoms, nuclei a little closer, looking a little bit like a positive charge. And even though two electrons repel, there's an overall attraction because this electron that's already gone through has attracted some positive neighbors. And so the new one that comes in sees the overall net positive and it sort of gets attracted to it, and it sort of follows the leader. It follows the first electron and it behaves like a pair. It's weakly bound to it because essentially it's following that net positive charge all the way through. So the two electrons begin to behave as a pair. It's called a Cooper pair. This is called BCS theory. One of the names is Cooper pair. He proposed this, right? And then you have to ask yourself, well, what would happen if two electrons, which normally repel, sort of start to behave like a single unit. Because two things in chemistry or physics are said to be bound together if they're in a lower energy state when they're together than if they're apart. These electrons, even though they normally repel each other, start to behave like in a lower energy state when they're together like this, but it's because of the first interaction sort of causing the second interaction to move along. But these two behave like they are a pair. So what you can do is you can sort of draw like a little circle around these things. And this is called a Cooper pair. And then you may have another Cooper pair over here, and another Cooper pair over here, and another Cooper pair over here. And the electrons stop behaving as single electrons that go through by themselves, and they start behaving in pairs. And it's just because you've cooled it down so much that the thermal motion of all the atoms normally going crazy have slowed down so that this effect can manifest. Without cooling it down, it won't manifest because the thermal motions will break this Cooper pair. The Cooper pair is very weak. It only exists at low temps because of what we said. And if you raise the temp a little, the agitation of the atoms will just break the whole thing, and then quantum mechanically they won't behave as a pair anymore. Now, remember what I said over here. I said bosons, an example of which is a photon, has a spin of 1. Electrons, an example of a fermion, is a spin of 1/2. But if you have two electrons that begin to behave like a single particle that's 1, then you have a spin of 1/2 and another spin of 1/2. What's that going to make? A spin of 1. It starts to behave, pairs of these things start to behave as photons, or similar to photons, right? So what you have is you have an electron, and you have an electron which are bound together as a pair. But this one has a spin of 1/2. And another electron, which it's bound to, has a spin of 1/2. And altogether, that makes a spin of 1. So it doesn't really behave totally like an electron anymore. It starts to behave like a boson. It starts to behave sort of like photons behave. Remember, photons can stack on top of each other. Photons can be in a low energy state. You know, the energy level diagram I drew, I showed you in a laser. They can be all in the same, you can have 1,000 trillion photons all on top of each other, all in the same energy state. So in this superconducting state, because the Cooper pairs are behaving like 1, it's sort of like a phase transition because the individual fermions are starting to behave not like fermions anymore, like bosons, like photons behave, kind of, right? And that means you don't think of them as two particles. You think of them as one particle with a spin of 1. And that one particle is already in the lowest possible energy state. It can't collide with anything and take any further energy out because quantum mechanically it's already in the lowest possible energy state. So they're all behaving like this, and so you start to think of, instead of individual electrons flowing through, you start to think of them as some other particle with a spin of 1, which can all be now on top of each other and behave totally different quantum mechanically, and they're all flowing through as sort of a fluid flowing through the superconductor together, and they're not interacting with each other. Why? Just the same way photons don't really interact with each other. They can be on top of each other. They don't collide. They don't lose energy. Photons, when you shine two flashlights, they don't like collide and lose energy. Because if they lose energy, then the color of the light would be different. The color of the light that we see is related to the wavelength, which is related to the energy. If photons collide, they would change colors. We don't see that ever. Shine two lasers, same color, they pass right through each other. Electrons, when they're bound in this Cooper pair configuration, can be right on top of each other, quantum mechanically. And you might say, that doesn't make any sense. I don't like it. Well, sorry. Superconductors are real. They are real. And none of you watching this, just like me, have ever really interacted with an electron on a one-by-one basis. Yes, my body is made of trillions and trillions of electrons, along with everything else. But I have never really played with a single electron. I don't really know how it works. I don't really know, or could ever examine, how it fundamentally behaves when you have two of them bound together like this. But the theory is that when they're bound together weakly like this, they behave not as electrons. They behave more similar to photons. So they don't bump into the other nuclei because the nuclei is so small that almost the whole atom is empty space. And they don't interact with other electrons because they're acting like giant spin 1 conglomerate particles. So you can almost think of the electrons not being individualized anymore. They're almost like a new particle, kind of like a dotted line around two of them, like a new particle that behaves kind of like a photon. And so they don't lose any energy as they sail through the superconductor. But if you warm the superconductor up, then you change the thermal agitation. This effect is broken. Cooper pair is broken, they suddenly behave like individual electrons. It just so happens in the history of mankind, we've only examined electrons individually. We never knew they could behave in a superconducting pair because we never could cool anything down before 1911 cold enough to actually see the effect, right? Now let me see if I said everything. So I guess the only thing I want to point to is that instead of behaving like this, like electrons in an atom, you can't stack them on top of each other. We did in this case, but they had different spins. But if you try to put another one, you can't because they have the same location and the same quantum thing. Now you might say, oh, the locations here is different than here, but remember, electrons are not balls, they're wave functions. The wave actually exists all the way around the atom. We just draw it as balls because it's kind of our best analogy, but they're not balls, they're waves that extend around the atom here. So these are kind of overlapping, but they are different spins, so they can do that. But we cannot put a third one. We have to do that by moving it farther away from the center. Whenever photons exist, they're literally all at the same energy. Oh, I drew them separate, but really they could all be on top of each other at the same energy, at same place, same time, same energy, same quantum states. The electrons can begin to behave like that, and that's how they can go through without any disruption. So we increase the temperature, we disrupt the whole thing. If we push too much electric current through, we exceed that critical current density. Remember I said there was a critical current, you can't go beyond that. Somehow, when you put too many electrons through, you disrupt the Cooper pairs. We don't know exactly how, and then that turns the superconductivity off. And the critical magnetic field does the same thing. When we have too much of a magnetic field, it generates eddy current somehow, which are so high that it disrupts the Cooper pairs, and so on. But I have to say, BCS theory is a theory for type 1 superconductors. It doesn't predict flux pinning. It doesn't predict, lots of other characteristics of type 2 superconductors. So we don't have a good theory for type 2 superconductors, but it's a good mental model to understand the basics. I bet that the type 2 superconductivity theory, once it's finally made, will have elements of BCS theory in it, but it will be modified slightly. That's just my guess. All right, I hope that you've enjoyed this. I have enjoyed teaching it to you. When I was in college, I used to make these things. I used to play with them all the time. It was super fun. I certainly didn't understand as much as I do now about them, but even now I don't know very much. I mean, honestly, nobody really does. But I hope that I've been able to summarize it in a way that was interesting for you. The main idea is that when you have a superconductor, the electrons that are going in do not behave like individual electrons. They start to behave like a collective fluid. And a collective fluid that behaves like a photon fluid. And I don't like using the word photon. Really, I should be telling you that they behave more like a boson. The electrons no longer behave as individual particles. They behave as sort of superconglomerate particles, which are kind of combinations of electrons that have different properties of their individual electrons. It's kind of like quarks. Quarks, there are 3 quarks in a proton and 3 quarks in a neutron. Quarks are different than the proton itself, but when they're combined in a certain way, they make this thing that we call a proton that has its own properties. When the different quarks with different characteristics are combined in a different way, they make this thing called a neutron, which is totally different. Well, under certain conditions, 2 of these electrons can pair up in such a way that as a unit, they behave more like a sea of boson-like substances that can then flow without any resistance because they are not interacting with each other. The electrons are not, as a pair, they're not interacting with their neighboring pairs anymore because they're all existing at the same energy level, much like the way photons do. All right, that's it. That's all I have. I'd love for you to leave me a comment. Let me know, was it too much? Was it too little, too detailed, too boring? Please let me know. Follow me on till the next one. Learn anything at mathandscience.com.